This is Mrs. T's Chem Talk Regents Review for Chemistry for the Solutions Review. In case you don't know who I am, I'm Beth Tuminello. I'm a chemistry teacher at Calhoun High School, and you can see some of my other videos on Mrs. T Chem Talk YouTube channel. If you just Google Mrs. T Chem Talk YouTube, you should come up with some other videos from me. So in order to get started with this particular video on solutions, we're going to talk first about some definitions, and the first thing is that a solution is going to be a homogeneous mixture, and it's composed of two or more substances mixed together, and they're going to be dissolved in each other, which means that they're evenly mixed. You can have a solution of two liquids, a solution of a solid and a liquid, or a solution of two gases, but the criteria is that the mixture will be homogeneous, which means that it will be evenly mixed completely throughout. The word homogeneous is a review word in this chapter. It can describe either a substance or a mixture. All substances are homogeneous. Remember, substances are elements and compounds. They're all homogeneous. A homogeneous mixture is a sample that's evenly mixed. The word heterogeneous, by contrast, can only describe a mixture, and it describes a mixture that has layers or clumps that doesn't fully dissolve. The word solvent is a word that we use in solutions, and a solvent is the liquid in which a solute dissolves, or if it's two substances that are in the same phase, it's the one that we have more of. The word solute is what gets dissolved into the solvent. For our purposes, it's usually going to be the solid that goes into the water. The word aqueous, which is going to be abbreviated AQ after a substance, tells us that this is a homogeneous dissolved mixture where the solvent is water. First thing we're going to talk about in terms of solubility is the table F. And for the first thing we want to note on table F is that we have two sections. We have a section that says ions that form soluble compounds, and we have a section that says ions that form insoluble compounds. So we will only have to find one piece of the compound in either the first column of the first chart or the first column of the second chart. So, for example, any ionic compound that has a group 1 ion, which would be Li, Na, K, CS, any of those elements that are in group 1, if they start an ionic compound, they're soluble no matter what, because there's no exceptions here. Anything that starts with NH4 is soluble because there's no exceptions. Anything that ends in NO3 or has CH3COO before it, or C2H3O2 at the end, HCO3 at the end, or ClO3 at the end, none of these have exceptions, so they're all soluble no matter what. However, if you have Cl in a compound, it's soluble unless it's AgCl, PbCl2, or Hg2Cl2. If you have SO4 at the end, it's soluble unless it's CaSO4, SrSO4, Ba, or PbSO4. So if you have something from both columns, it's the opposite of the top. If you have something just from the first column, it's what it says at the top. For example, if we want to use table F to determine the solubility of NaNO3, it said that Na plus is a group 1 ion, and group 1 ions are soluble with no exceptions. So this particular compound is soluble. Same thing for K. Na and K are both group 1 ions, so this will be soluble as well. If we go back, however, to the chart here, sorry about that. If we are looking for AgCl, we have Cl here as something that is generally soluble, but Ag is one of its exceptions, which means that AgCl will be insoluble. And if we go back again, for PbSO4, SO4 is usually soluble, okay, but Pb is one of its exceptions, so we'll also say that PbSO4 is insoluble. When we look at a precipitation reaction or a double replacement, we are going to look up these compounds on table F and see whether they're soluble or insoluble. And when we decide whether they're insoluble or soluble, if they're soluble, we'll actually put a Q. If they're insoluble, we'll actually put an S for solid, because insoluble means that they don't dissolve. So if we look at KNO3 and AgSO4, K is a group 1 ion, so KNO3 is automatically soluble. AgSO4 is also going to be soluble because Ag is not one of sulfate's exceptions. So we're going to write AQ for each of these. Now this is one of those inners and outers. So the K goes with the SO4. The Ag goes with the NO3. We re-crisscross and drop the signs, and that's how we got K2SO4. This was a +1 and a -1, so that's why it got to AgNO3. This was a +1 and a -2, that's why it's K2SO4. So we're going to look up AgNO3 and K2SO4 back, oops, wrong way, on table F. So again, K is a group 1 ion, so that's soluble no matter what. SO4 is also something that's soluble with that. And then, I'm sorry, what was the other one? Was AgNO3. These are all soluble. So since NO3 is soluble with no exceptions, and since K is soluble with no exceptions, that means that these are aqueous, and that actually means that this reaction is not really driven to happen because it's not making a precipitate. But all of these are soluble on table F. Now AgNO3, NO3 is soluble with no exceptions, so we're going to put aqueous. K is soluble with no exceptions, so we're going to put aqueous. Ag goes with the Cl. K goes with the NO3. We crisscross and drop the signs. K and NO3 are each soluble with no exceptions, but Cl is soluble and Ag is one of its exceptions, so we're going to put solid here. And since this is solid, we're going to call this one the precipitate. Because this is a precipitate, that means that we could filter this out with filter paper. It does not dissolve, and it would settle to the bottom. When we talk about electrolytes, only soluble ionics for our purposes in this chapter are electrolytes. And they are electrolytes because they dissolve in water to conduct electricity, and they conduct electricity because of their mobile ions. So you should have table F out, and only species or compounds that are on table F that are soluble will be electrolytes. So since this one is soluble, it's an electrolyte. Pb3PO4 is insoluble, so it's not. AgOH is insoluble, so it's not. Calcium acetate is soluble, so it's an electrolyte. Ammonium sulfide is soluble, so it's an electrolyte. Again, that's going to be using table F. Anything that's soluble on table F will be considered an electrolyte. When we talk about table G, we have the solubility curves, and this table G is going to plot for us the maximum amount of solute that can dissolve in 100 grams of water at this temperature. And if we look at this, a saturated solution is a solution that's at equilibrium, and saturated is going to be anything that falls on the line. This is actually a plot of saturated solutions. Unsaturated solutions would be for this particular, if we're talking about potassium nitrate, anything that is less grams than on the line would be considered unsaturated. So this whole section here would be unsaturated for potassium nitrate. And for a supersaturated solution, we actually have to heat the solution up and dissolve it and then cool it slowly, so that we actually kind of trick the solution into keeping the extra solute. So in order to have a supersaturated solution, you actually have to heat it, get some extra solute to dissolve, and then cool it very slowly, or disrupt it in some way, all of the extra solute will fall out of solution. We'll actually see it rain or fall to the bottom of the container. You determine what type of solution you have using table G by looking up the temperature and the number of grams dissolved and plotting it as a point. If that point is below the line for the substance in question, it's unsaturated. If it's on the line for the substance in question, it's saturated. And if you've heated it and cooled it slowly and that number of grams is above the line, that would be a supersaturated solution. We have mostly solids on this chart, and solids are the ones that increase in solubility as we increase the temperature. And for our gases, those are the ones that get less soluble as we increase the temperature. So anything that goes in an upward slope is a solid. Anything that goes in a downward slope on this chart is a gas. So for example, some questions that you might have to answer. How many grams of potassium chloride can be dissolved in 100 grams of water at 80 degrees Celsius? So you're first going to find potassium chloride, which is KCl. Then you're going to find the temperature and the number of grams, the temperature that they tell you. They say 80 degrees Celsius. And we're going to see where 80 degrees Celsius crosses that line. And I'm going to say it's at about 52 grams. Now, certainly this is a very small version of table G here, so it might be a little bit more or less than that. I can't really tell on my graph here. Because it says 100 grams of water, it means that we can use this table directly. If we wanted to know how many grams of potassium chloride at the same temperature can be dissolved in 200 grams of water, if we double the water, we double the amount that can dissolve, and that would be, that would be 52 times 2, which would be 104 grams. And if we wanted to find out after we make this solution at 80 degrees Celsius and 100 grams of water, which would dissolve 52 grams, how much would come out if we cooled it to 50 degrees Celsius? Oh, this is a different substance. Crud. Hold on. So for this one, this question, if we look at it actually, it says a saturated solution of potassium chlorate is formed from 100 grams of water. If the saturated solution is cooled from 80 to 50, so we now have a different substance. So potassium chlorate and potassium chloride are two different substances. And potassium chlorate is the one with the ClO3, right? 8 means that it has to have oxygen in it. So at 80 degrees Celsius, I form a saturated solution of potassium chlorate, and that looks to me that that's about 45 grams that can dissolve. We cool it down to 50, and at 50, about 21 grams can dissolve. So the amount of precipitate that forms will be 45 minus 21, which means that 24 grams of salt will come out of solution when we decrease the temperature like that. When we talk about molarity, molarity is a way of finding concentration, and this is on table T. Molarity is moles of solute over liters of solution. So we're going to write big M equals moles over liters, and they want to know the molarity where 1 mole of sodium chloride is dissolved in 1 liter of solution, and that would be 1 molar. And if they want to know how many grams of sodium chloride that is, 1 mole of NaCl, we would have to find the gram formula mass, which is Na times 1, Cl times 1, and we're going to add those up. That 23.0 and 35.5, and when we add them up, we get 58.5 grams for the mass of 1 mole of that. And if they ask you a question backwards, again, molarity equals moles over liters. How many moles of potassium nitrate? That means that the X is my potassium nitrate. Can be used to form or prepare 2 liters of a 0.5 molar solution. 0.5 equals X over 2. 0.5, if we cross multiply, we get X equals 1 mole. Also have the formula for parts per million. Parts per million also is on table T, which is mass of part over mass of whole times 1 million. 1 million has, 1 million has 6 zeros. So when you plug it in, you're going to do 1, 0, 0, 0, 0, 0, 0 when you're multiplying by 1 million. And if we want to do a problem, we have 4.4 times 10 to the minus 3 grams in a 1 times 10 to the third gram sample. We're going to do the part over the whole times 1 million to get our parts per million. And when we do that on the calculator, we do 4.4 times 10 to the minus 3 divided by 1 times 10 to the third, and we multiply the whole answer times 1 million. We get the answer as 4 parts per million. 4.4 parts per million. Remember, parts per million is used when the concentration is really small, and where using percent would give us such a small number, it wouldn't really mean anything to us. It would be hard to work with those numbers. When we talk about freezing point depression and boiling point elevation, whenever we look at a thermometer, let's say this is 0 degrees Celsius, and let's say this is 100 degrees Celsius. These are the normal freezing and boiling points of water. If we add, let's say this is pure water, if we make a solution, we add something to the water, what's going to happen is that the boiling point and the freezing point are going to get further away from each other. So the boiling point is going to go up and the freezing point is going to go down. That's why we say boiling point elevation, because it goes up when we add something to water, and freezing point depression, because freezing point goes down when we add something to water. The more concentrated the solution is, the more the freezing point goes down and the more the boiling point goes up. So ionic substances tend to affect boiling point more because they break up into pieces, different ions, whereas covalent substances tend to affect boiling point less. And the more ions a substance breaks up into, the more it can conceivably affect the freezing and boiling point. So that's the end of the solutions review. Kind of touched on the different things that we did in solutions in our class. If you have any other questions, certainly feel free to come to Extra Help, come see me, ask me questions, but hopefully this was helpful for you. Have a good day.